Okay, so good day. So in this video, we will discuss the relationship between different types of latitudes. So at the end of this topic, students should be able to solve one kind of latitude from another kind of latitude. So first, we have the types of latitude, and second is the difference between each latitude. Okay. So here shown the meridian ellipse, or the cross section of your of the figure, your mathematical figure, which is the ellipsoid. So here's your meridian ellipse. Okay, so that we have your point P as the point we are referring or in question. Okay, so we have here shown in red variables. So we have one, two, and three types of latitude as shown here. Okay, so we will uh, state them one by one. So in our previous slides, we show you that we have three latitudes. So so therefore, in order for us uh, to define point P in terms of latitude, we can define this point by these various latitudes. So what are the difference between them? So first, we have the geodetic latitude, represented by variable phi, or Greek letter phi. So it is the direction of the ellipsoidal normal relative to the plane of the equator. So from your uh, equatorial plane, so your equator, going to your normal. So when I say normal, meaning to say at this point, we project a normal line. So that normal line is perpendicular at this point. Okay, then projecting a radius of what we call uh, the radius of curvature. Okay, so that's your geodetic latitude. So the next one, we have the geocentric latitude. So it's the angle of the line connecting the point, let's say point P, okay, with the origin, then relative to the plane of the equator. So at this time, so instead at we're focusing on the same point. Instead of projecting a normal line, we direct its line from point to the origin. So forming this line, okay, okay. So forming that line, then uh, the angle projected by this figure from the equator going to that line, that is your geocentric latitude. Okay, so when we say origin, that is the center, right? So where is the your x, y, z is 0, 0, 0. Okay, so therefore, that is your geocentric. Let's say that is the projection of your geocentric latitude. For geodetic, so with focusing at the same point, we project a normal line, okay, going to the center. Not center, but going or intersecting the rotational axis. So this one. So this axis, okay. So as you can see here, this is the image, okay, or this is the figure. So and so this is the geodetic latitude, and this is the geocentric latitude. So they have different um, projection, so they are not equal at some point. Okay, so the question is, at which latitude, let's say, when these two values would be equal, no? So those kinds of questions. So try to analyze, then you will have your answer. Okay. Then the third one, we have the reduced. So it could be theta or beta. So most of the references uses beta as the variable for this kind of latitude. So we have point A here. So point A is projected, okay, uh, projected upward until intersecting the sphere or circle. So this circle radius is equivalent to A, right? So A, uh, that is your semi-major axis length. So the radius of this one, this circle, is A. So here we have the same point, but we project it up. We project it until we intersect point A. So how do we project this one? That is parallel to your rotational axis. So once we intersect that one, then we have your point here. Then from here, that is normal, okay? Then we project it to the center, so thus forming a line, and we project the um, reduced latitude, okay? So it is the angle at the origin and in the meridian plane from the equator to the radial line that intersects the projection of the point along with the perpendicular to the equator. So at the sphere of radius equal to the length of semi-major axis of the ellipsoid. Okay, so if this is A, this this length from A to O is equals to A. So okay, so again, reduced latitude is used only in theoretical contexts. So in maps like geographical, that is geodetic or sometimes ellipsoidal, latitude is used. So geocentric latitude appears in practice only in satellite and space geodesy. So most global navigation satellite system applications utilizes the geocentric kind of coordinate system. Okay. So now here are the relationships between different types of latitude. So shown here, tangent psi is equals to, or tangent to your geocentric latitude is equals to b over a. So remember b, that is your semi minor axis. So which is from your origin to this point. So that's your b, and your a, as said lately. So this is a. Okay. So if you're given uh, any kind of latitude and you are given parameters, then you can solve the other latitude given. So A, that is your semi major axis. Okay. So now to determine your uh, uh, reduced latitude equivalent, so you just simply manipulate the formula. Okay. Then we have here tangent of your geocentric latitude is equals to b squared over a squared times tangent of your geodetic latitude. So if you try to solve the values, so it should be like this. So it is always your geodetic latitude is the highest, or I mean, is the largest in value, or yeah, largest in value, and there are times that they will be equal, right? So your geodetic latitude is greater than or equal to your beta, and your when beta, that is your reduced latitude, and your reduced latitude is greater than or equal to your geocentric latitude, no? So you can try, you can also prove that one, no? If you have some, for example, if you use let's say WGS 84 parameters for A and B, then get an example like uh, what if your geocentric latitude is 30 degrees? So how much is your reduced latitude? So it should be, your reduced latitude should be greater always. If not equal, it should be greater. So something like that. So these are the relationship between the three latitudes. Okay. So okay, so we have here a simple example. So let's say a point on the ellipsoid has a geocentric latitude of 45 degrees north. So if the flattening of the ellipsoid is this value, so we are asked to compute the values of the geodetic and reduced latitude. So we are given, okay, we write down a given, your geocentric latitude, which is equals to 45 degrees north. And what else? The inverse flattening. So this is inverse, the inverse flattening, okay? So that is 1 over f. So 1 over 9786982. Okay, remember flattening is unitless, and it's the measurement of the flatness, no, of your sphere. So how ellipse this sphere is, right? So we are required to determine the following. So what? So the geodetic and your reduced latitude. Okay. So we write down first the formula. So we have your solution. So tangent phi is equals to um, b over a tangent beta. Okay. So we are concerned with the beta. So we just simply manipulate the formula. So that would be become arctan. So a over b, then tangent of your uh, geocentric. So but before we proceed, okay, before we proceed on solving for beta, so uh, we don't have yet the formula, or let's say the values for a and your semi minor axis. So if we draw the figure, okay, so it should be at first we draw the figure, but anyways we can still catch up. So for example, we are given the geocentric one, this. So let's say here, that is your 45 degrees geocentric. So we are asked, so we assume that we have this sphere, okay. Then we have your projection here. Let's say that if this is P, this is P prime on the sphere, then boom, you have your this one. This is now your reduced. And for the geodetic, so this is your axis. So we, for example, that one, so normal. Okay, so let's try another color. So this is your geodetic latitude. So here so this value or this angle, that is your geocentric. Okay, so somehow the drawing is not clear. Let me redo it for you. Okay. Okay, so let's try this one again. Okay, so we have then let's use another color so that we have, okay, okay, okay. So for example, this is the point, no, the geocentric one. Okay, this is the point. So this is geocentric, which is 45 degrees. So we project point here. Let's say if this is P prime, then going to the center. This is your reduced latitude. Another one, we project normal to this point. So this is your, okay, so that this is your geodetic latitude. Okay, so the figure is clear. Then next is we need to solve first for the values a and b. Okay. Okay. So now we are given the values of flattening. Okay. So flattening. So flattening is equals to 1 minus b over a, right? So this is your flattening. So instead we use uh, use a and b, we can use the flattening, right? So we just manipulate the formula. So that would become b over a is equals to 1 minus f. And that would become a over v, that would become 1 over 1 minus f. Okay? So remember, we are already given this value. So we can substitute, instead of a over b, we can use this value. Okay? So now, let's proceed first. So to determine your um, reduced latitude, that would be equal to arctangent 1 over 1 minus f times tangent of 45 degrees. So 1 over 1f is equals to 1 over 1 minus, uh, so if we transpose this one, okay, also correction, this is not the inverse flattening, but it's the flattening. Okay, this is f. Okay, therefore your flattening we directly substitute this value, 1 over 294.9786982. Okay, so that would be equals to, let's try to calculate. So that would become 1.003401.607. So, okay. So now, when we try to solve for beta, so beta would be equals to, so we directly solve for it. Our tangent of the answer, which is 1.003401.607 times tangent of 45 degrees. So the answer is, your reduced latitude is 45 degrees 5 minutes and 50.22 seconds. So that is your beta. Okay. Okay, so for the third one, we have this. For the third one, we use this equation again. So tangent v is equals to b squared over a squared tangent your geodetic latitude. So same principle or same method. So we directly have this equation, -1. So now this is squared. So we can utilize this equation. So we square this value, it would become a squared b squared is equals to 1 over 1 f squared. Okay, so now this would become a squared over b squared tangent geocentric. Then that would become arctangent. So we put a bracket there. And then we substitute this variable into this one. So that would be 1 over 1 minus f squared times tangent 45 degrees. So if you continue to solve this one, okay, that would be equals to, okay, okay, so this would be equals to 45 degrees 11 minutes 40.44 seconds. So that is your answer. Okay. So if you have question, you can use the consultation form, so that if you have some queries to this example, You can raise it there, or you can post your comments on the comment section. So here, these are the differences of various latitudes. So given that we use the Clark spheroid of 1866, so the maximum difference between the geodetic and reduced latitude is 5 minutes and 50 seconds, meaning this is the maximum difference that we could attain if we have this spheroid, if we use the spheroid or ellipsoid. And for the difference or maximum difference between the geodetic and geocentric is equals to 11 minutes 40 seconds. So this is somehow the maximum difference that we could attain using this ellipsoid. Okay, so if we use other ellipsoid like GRS 80 or WGS 84, so probably they will have a slight difference, but somehow the values will be close to these differences. Okay, so meaning to say, as your, let's say, if we put reference of our geocentric latitude as your uh, latitude, geocentric latitude increases, diba? At the same time, your geodetic and reduced latitude also moving or increases. But there are certain points that it will attain only this maximum differences. No? So try to analyze, like, for example, what is the difference between these angles if your geocentric angle is 30 degrees, what if 60 degrees? So you will see, if you want to jot it down, like at 15 degrees, what is the difference between the two? At 75 degrees, what is the difference? So you will know the graph between the differences, right? So here, the closest differences can be attained not exactly, but at near 45 degrees. Okay? So, mean to say, somewhere in 45 degrees, that is where your maximum differences can be obtained. Okay? So, to review, so we already discussed the different types of latitudes. So that is, we have first the geodetic. So that is by phi. Next, we have the geocentric. That is psi. And the third one is reduced. Somehow it is called the parametric latitude, represented by beta. Okay. So also you are already shown how to convert latitude from one kind of latitude to another kind of latitude, or vice versa. No. So the importance of the conversion is you need to have at least the ellipsoidal parameters. So it could be the flattening, or it could be the semi-major or semi-minor axis. So at least, no, if you are given the eccentricity, score the eccentricity, still you can solve for the conversion, because these four variables have a relationship. No, they have relationship to each other, so you can either manipulate the formula so that you can solve for the conversion as needed. Okay, so if you have some questions, just type into the uh, in the comment section, or you can contact me using the online consultation form. So we have the references for this lesson, and thank you for watching.